Well, here I want to talk more about the coagulation process. And for illustration purposes, I have 4 jars that have negatively charged colloidal matter in each of them. All of these particles carry the negative charge. They repel one another, and that repulsive force is called zeta potential. And the zeta potential can be measured to determine the extent to which the particles are carrying a negative charge, or the negative charge within the solution. Well, in order to overcome that zeta potential so that these colloids can come together and form microfloc and then macrofloc so that they can ultimately settle out, we need to neutralize the negative charge. So we do that by the addition of positive ions. And aluminum sulfate, for our purposes here, will be what we add. So when we add the alum to one of these jars, we see that positive ions from the alum react with the negatively charged colloids, and that effectively neutralizes the charge. So we call that step charge neutralization. Now that takes 1 to 2 seconds to occur. So once we rapidly mix the coagulant in the solution, within 1 to 2 seconds we've achieved charge neutralization. And there's different degrees of coagulation. This is how we classify the extent or the degree of coagulation. And it's based on the zeta potential. Well, here you can see this chart in the upper left-hand corner where we have the different degrees of coagulation being maximum, excellent, fair, and poor. So starting at the bottom, poor coagulation would be if we had a zeta potential in the range of -20 up to -11 millivolts. As we lessen the negative charge, as the negative numbers get smaller, for example, going up to fair, going from 10 to -5, that's considered fair coagulation. And then as we further reduce the zeta potential to -4 to 1, or a range of -4 to 1, we consider that to be excellent. And most plants will operate slightly negative here, so this excellent degree of coagulation is where most plants operate because they don't want to add too much coagulant, because it can then pass through the plant and end up causing issues in the distribution system. And then our final classification of maximum coagulation is when the average zeta potential is in the range of 0 to +3. So you might want to remember that for your exam, the different degrees of coagulation. Well, now that we've neutralized the charges, there's this thing called van der Waals forces that come into effect. Now, van der Waals forces is the force between all objects that tries to pull them together. So it's not until van der Waals forces overcomes the zeta potential that these colloids can come together and form a flock. So by neutralizing the zeta potential, van der Waals forces can then go into effect and our microfloc can become macrofloc. Additional chemical in the form of polymer, and a cationic polymer is typically used in the coagulation process, and that helps keep that flock together. Flocks gently mix and collide in the flocculation process. They get even larger, and then ultimately they'll settle out in the sedimentation process. So to kind of get an idea of how this process works, on the far left, we start with charged colloids that are repelling one another due to the zeta potential, and they will not come together. Then in the next jar, we see that coagulation occurs once we add the aluminum sulfate, or whatever the coagulant is that we add, because of the addition of positive ions. Then in the next jar, we see flocculation begin to occur, where the microfloc becomes macrofloc and even larger, so that it can then settle out. And in this final jar, we see the sedimentation process. So this is a brief overview of what happens during the coagulation and flocculation process, and then ultimately sedimentation.